All right, let's talk about one of the coolest, most intuitive tools in all of AI, the decision tree. We're going to pull back the curtain and see exactly how an artificial intelligence actually learns to make a choice piece by piece.
So let's start with that big fundamental question. When you ask an AI to predict something, how does it actually land on an answer? I promise you, it's not some kind of black magic. It's actually a really structured process that might feel surprisingly familiar. I mean, think about it. You do this every day. You're hungry. Do I want something spicy? Nah. Do I want something fast? Yeah. Okay, should it be healthy? Maybe. See, every question takes you down a path, getting you closer to a decision. A decision tree in AI works the exact same way. Just a series of simple questions to sort through the data. So first, let's get a handle on the basic structure. You can really just think of it as a simple map for making any decision. Every single decision tree is built from three core parts. You start at the top with the root node. That's your big opening question. The different answers to that question create the branches. They're the paths you can take. And when you follow a path all the way to the end, you hit a leaf node. And that's it. That's your final answer, your prediction. Root, branches, and leaves. That's the whole anatomy.
So the flow is super straightforward. A piece of data comes in at the top, at the root. The tree asks its first question. Based on the data's answer, it gets sent down one of the branches. That continues until it can't go any further. It's reached a leaf. And that leaf tells you the final classification.
Okay, so what's the whole point of this? What's the tree actually trying to accomplish? Well, it's all about creating what we call pure groups.
And this is where the real intelligence comes in. This is the magic of the model. Out of all the possible questions it could ask about the data, how does it figure out which one is the best one to start with? Which question will do the best job of untangling everything?
The secret is this constant drive for purity. A perfect split, a perfect question, is one that creates new groups where everything inside that group has the same outcome. The whole game is to ask questions that just get rid of as much ambiguity as possible.
And this slide lays it out perfectly. Look at the left. An impure group is a mess, right? It's a mix of yeses and nos. You can't be certain. But on the right, that's a pure group. It's totally uniform. Every single person in that group has the same outcome. The job of the decision tree is to ask smart questions that turn those messy, impure piles of data into these nice, clean, pure ones.
So, we know the goal is purity. But how does the tree mathematically figure out the best question to get there? Okay, let's get our hands dirty and look at some actual data.
We're going to use a classic example that's perfect for this, predicting whether to play tennis based on the weather. Our mission is to predict that very last column, play tennis. The other columns, outlook, temperature, and so on, those are the features, the tools our tree can use to ask its questions.
Now, the algorithm is incredibly methodical. It doesn't just guess. It basically holds a competition. It systematically tests every single feature to see which one would make the best starting question. It asks itself, okay, if I split all my data based on the outlook, how pure will my new groups be? Now, what if I split by humidity instead? This is the exact challenge the algorithm has to solve. Which one of our weather features is going to do the best job of separating the yes, let's play tennis days from the no, let's stay inside days, right from the very start? To figure that out, it's got to have a way to keep score.
So, to compare all those possible questions, the algorithm needs a way to score them, and it does that by measuring impurity. Okay, you're going to hear a couple of kind of technical-sounding terms here, entropy and Gini impurity. But don't let the names throw you. All they are just fancy mathematical ways to put a number on how mixed up or messy a set of data is. That's it. A high score means lots of disorder, a very impure group. A low score, especially 0, means perfect purity.
And look, you really don't have to get bogged down in the complex formulas here. As this quote from the source material points out, they're all pretty much trying to do the same thing. The big idea, measuring disorder, is what's absolutely crucial, not memorizing the specific math behind each one.
The whole point of measuring impurity is to calculate something called information gain. And this is the key. This is the algorithm's secret weapon. It measures the impurity before asking a question, and then it measures the impurity of the new groups after asking the question. That drop in messiness, that reduction in impurity, that is the information game. And the algorithm is simple. It always picks the question with the highest information gain. Okay, let's recap. We have our goal, create pure groups. And we have our tool for getting there,
maximizing information gain. Now let's watch how the algorithm puts it all together to build a tree, step by step.
The process it follows is known as a greedy algorithm. And all greedy means is that at every single step, it makes the best possible choice for right now, without looking ahead. It wants that immediate reward. So it just calculates the information gain for every feature, picks the winner, splits the data into new piles, and then for each of those new little piles, it does the exact same thing, rinse and repeat all the way down.
And voila, here are the actual results for our tennis data. The algorithm runs the numbers for every feature. And look at that. Outlook is the hands-down winner. It's not even close. It gives us the biggest reduction in impurity, the biggest bang for our buck, with a score of 0.246. And just like that, the first decision is made. Outlook becomes the root node of our tree. The entire dataset is now split into 3 new branches based on the answer, one for sunny, one for overcast, and one for rainy. And from here, the algorithm will run the exact same competition again for the sunny group and the rainy group to find the next best question to ask them.
So you can see why decision trees are so popular, right? They're incredibly intuitive, they're powerful, and you can literally see the logic. But like any tool, they're not perfect. They have their trade-offs.
The biggest pro is definitely how easy they are to interpret. They're what's called a white box model, because you can see right inside and follow the logic from start to finish. But the biggest con, the thing you always have to watch out for, is something called overfitting. This happens when the tree gets too specific and basically memorizes the training data, including all the random noise and weird quirks. And when it does that, it becomes terrible at predicting anything new that it hasn't seen before.
And that leads us to one last really interesting thought. We've seen how a single tree works. It's pretty powerful, but it can make mistakes. So that begs a fascinating question. If one tree can give you a decent answer, what could you accomplish if you combine the votes of hundreds or even thousands of different trees? What happens when you decide to build an entire forest?